Welcome friends. In this new video we see what is meant by exact differential equation. Here we see condition of exactness of first order differential equation to be exact, and we see few examples of exact differential equation, and we discuss about solving that exact differential equation. The definition of exact differential equation is a differential equation which has been formed from its primitive by differentiation and without any further operation of elimination or reduction is called as a exact differential equation. A differential equation which has been formed from its primitive by differentiation by differentiation and without any further operation of elimination or reduction is said to be exact. So this is an exact definition of exact differential equation. So we consider the exact differential equation in this form: m dx plus n dy. Here this is an equal to 0. This equation to be an exact, it must be formed from its primitive by direct differentiation without any operation of elimination or reduction. Suppose it is obtained from a function u by direct differentiation. So we consider that. So let us suppose that let it is obtained, it is derived from u. U is a function of x and y. As it is derived from, it is directly obtained from u by differentiation. So we write this as a du equal to m dx plus n dy. But we know that the total derivative of u, here we have taken u is a function of x comma y, and as it is we have considered this is an exact differential equation. Whenever it become exact, when it is obtained from some function directly without elimination, without reduction. So we consider this u as a function of x and y, and it is direct derivative. So du equal to m dx plus n dy, and but we know that total derivative of u equal to del u by del x into dx plus del u by del y into dy. Okay. So du equal to del u by del x into dx plus del u by del y into dy. Now look at this. When we equate this, we get m equal to del u by del x and n equal to del u by del y. This is suppose equation number 1, and we get this m equal to del u by del x and n equal to del u by del y. This is called as a necessary condition that m dx plus n dy to be an exact. This is a necessary condition, m equal to del u by del x plus and n equal to del u by del y. Now, we know that if we differentiate this with respect to y, that is del m by del y equal to, this is equal to del 2u by del y del x, and we differentiate this with respect to x, del x del n by del x equal to del 2u by del x del y. But friend, del 2u by del y del x and del 2u by del x del y are equal, and therefore we get that del m divided by del y equal to del n divided by del x. So, whenever this condition is satisfied, this is called as a sufficient condition of exactness, sufficient condition for exactness of a function that satisfies equation number 1. Okay. So, we have necessary condition, that is m equal to del u by del x and n equal to del u by del y, and sufficient condition del m by del y equal to del n by del x. Whenever equation 1 is exact, then this condition must be satisfied, del m by del y equal to del n by del x, or whenever this condition is satisfied, equation 1 is called as a exact differential equation. Now, let us find the function u. How to find the function u? So, come to this definition once again. You can see that this del u equal to m dx plus n dy. Let us clear this, and here we clear this part, and you can see that this del u by del du equal to this m dx plus n dy. Now, we integrate this with respect to x, so that we get here u equal to integration of m into dx plus. Now, we do not integrate this totally, we take only those terms from this that do not contain integration of those terms not containing x, and we integrate this with respect to y. So, we find this u by this integration, by direct integration, here du equal to m dx plus n dy. But integration is like this, integration of m dx, this is with respect to x, we are integrating with respect to x, and but from the second term we are taking only those terms not containing x, and we integrate this with respect to y. That means it contain only the terms of y, and therefore we can write it as a function of y, f of y. So, what we get? We get here u equal to integration of m dx plus f of y. Now, let us find this value of f of y. Differentiating this, let us call this equation number 3. Differentiate 3 with respect to y. What we get? Differentiating with respect to y to 3. Okay, we are differentiating 3. Then what we get? Del u by del y equal to del by del y of integration of m dx plus, this is function of y only. So, here we have total derivative d by dy of f of y. Okay. Here it may be function of two variables, but here this is only function of single variable y, and therefore we write here total derivative d by dy. Look at this, what is del u by del y? Del u by del y equal to n. Here n equal to del by del y integration of m dx plus d by dy of capital F of y. Now friends, when we differentiate this once again with respect to x, this is equation number 4. Let us differentiate this with respect to x. Then what we get? We get here, I am differentiating, I am del by del n by del x equal to del n by del x here, or we can change the order. So, del by del y into del by del x of integration of m dx plus. Now, this is function in this 4 equation, this is total function of y, and therefore, when we integrate differentiate with respect to x, y treated as a constant, so its derivative equal to 0. Now, here you can see that this is a integration with respect to x and we are differentiating with respect to x. So, derivative and integration get cancelled and we get del n by del x equal to del m by del y, that is the condition of exactness. Del n by del x equal to del m by del y, we get these conditions. Okay. Here therefore, to find this value of f of y, you can see that here what we get this equation del u by del y equal to, that is n equal to del by del y of m dx plus this d by dy of f of u. Now, here we integrate this. Okay. So, let us write this value as what is d by dy of f of y, equation number 4 equal to n minus del by del y of integration of m dx. Look at this. Okay. Now, let us integrate this with respect to y. Integrating with respect to y, derivative and integration get cancelled and we get f of y. F of y equal to integration of n minus del by del y of m dx with respect to y. Look, okay, n minus these terms, n minus del by del y of integration of m dx into dy plus integrating constant a. So, from this we can write this u equal to integration of m dx plus f of y in this equation number 3. Let us put the value of f of y, integration of n minus del by del y of integration of m dx into dA plus dy plus integrating constant a. So, this is the function from which we have obtained our exact differential equation m dx plus n dy equal to 0. Now, instead of differentiating, we can also find this as integration n dy plus integration m minus del by del x of integration of n dy into dx equal to c. So, this is the function n into dy plus m into del by del x integration of n dy into dx equal to c. Here we obtain by applying the same method and this equation integrating constant c. So, what is the exact rule of finding or showing whether the equation is an exact differential equation, or when the equation is an exact differential equation, how to find the solution of that exact differential equation. So, in short, we can write the solution by following this rule. First, integrate m with respect to x. This is the first term, first step. Then second, integrate those terms of n that do not contain x. do not contain x, and this integration is with respect to y, that is the terms from the n that do not contain x, and equate this, that is 1 plus 2 equal to constant. This is the third step of finding the solution. So, this is the very short rule of finding the solution of exact differential equation. What is the exact rule? First we have to integrate m with respect to x, then we have to integrate those terms of n that do not contain x, and third, first plus second equal to constant. So, let us see example. This is a very simple process of exactness. X square minus 4xy minus 2y square dx plus y square minus 4xy minus 2x square into dy equal to 0. So, if we compare this equation with m dx plus n dy equal to 0, you can easily calculate the value of m equal to x square minus 4xy minus 2y square and n equal to y square minus 4xy minus 2x square. Here we have obtained the values of m and n. Now let us check whether this equation is an exact or it is not an exact differential equation. To do that, so let us calculate their derivatives, del m by del y equal to, when we differentiate with respect to y, x is x remain constant. So, derivative of this term equal to 0. This 4 and x both are constant. So, minus 4y and 4x minus 4x, and derivative of this term minus 2 into 2 4y. So, we get here derivative minus 4x minus 4y. Now, del n by del x, when we differentiate with respect to x, y is a constant term. So, derivative of this is 0 equal to, and here 4 and y are constant. So, minus 4y and minus here minus 4x. Look at this, minus 4y 4x minus 4y 4x. So, here del m by del y equal to del n by del x. Condition is satisfied, therefore, given equation is an exact differential equation. Okay. So, let us apply the rule to find the solution. Given equation is an exact differential equation. What we have to do first? We have to find the integration of first step here, integration of m with respect to x equal to integration of which term, x square minus 4xy minus 2y square into dx. This is equal to integration of x square, x cube divided by 3 minus 4 into y, constant, integration of x is x square divided by 2 minus 2 and y square constant. So, integration with respect to is x. Okay. So, we get this x cube divided by 3 minus here 4 and 2 get cancel and we get 2 x square y minus 2x y square. This is the integration of m. And now, second step, integrate those terms from n that do not contain x. Look at this n. When we see the value of n, we have here this term contain x, this term contain x. Therefore, in this, those terms from n that not containing x, integration not containing x, remember this, those terms from n that do not contain x and integration with respect to y. So, this is equal to integration of only y square with respect to y, and that will be y cube divided by 3, y cube divided by 3. Now, solution of this equation is, what is third step? First plus second. First, what is the first? X cube divided by 3 minus 2x square y minus 2y square plus y cube divided by 3 equal to constant. This is the solution of this exact differential equation. So friend, the process is a very simple. You can see that how we have obtained the exact differential equation and the procedure of solution of exact differential equation. Let us see one more example of exact differential equation and obtain the solution of that exact differential equation. So, let us select first. We have selected, let us delete this and let us see one more example here. X square minus 2xy minus y square into dx plus minus x plus y whole square into dy equal to 0. Now, from this, compare this equation with m dx plus n dy equal to 0. Here we have capital M equal to x square minus 2xy minus y square and capital N equal to minus x plus y whole square, and this is equal to minus x square minus 2xy minus y square. Let us check the condition of exactness, that is differentiation of m with respect to y. This is constant differentiation, this is constant, so minus 2x and minus 2y. Del n by del x equal to minus 2x, y square is constant, so its derivative is 0, and minus 2y, minus 2x minus 2y, minus 2x minus 2y. So, therefore, we have seen that this equation del m by del y minus 2x, this, that is del m by del y equal to del n by del x. Condition is satisfied and therefore, the given equation is an exact differential equation. Now, to find the solution, first let us integrate m with respect to x. So, that integration of m x square minus 2xy minus y square into dx equal to integration of x square, x cube divided by 3 minus 2 x square divided by 2 into y, y is constant, minus y square, y square is constant. So, integration with respect to here into x, 2 get cancel and we get x cube divided by 3 minus x square y minus y square x. So, this is a m. Now, in the second step we have to integrate those terms from n that do not contain x. Here you can see that this term contain x, this term contain x. So, leave these terms and integrate those terms that do not contain x, that is y square into dy. So, this will be minus y cube divided by 3. We get this y cube divided by 3. Now, here you find the solution. In the third step we have to add these two and equate constant. So, x cube divided by 3 minus x square by y minus y square x minus y cube divided by 3 equal to c. This is the solution of a required differential equation, exact differential equation. So, friend, we have seen the definition of exact differential equation. We have seen the method of finding the solution of exact